about the equation. Isn't it in vertex form? Yeah? Okay, so these ones are the easiest ones to solve. We only just isolate the squared part. So we would add 4 to both sides of the equation. Now on the left, we have an x minus 6 squared is equal to 9. Now, it's this square, so to undo the square, we can square root both sides of the equation, right?
Yep.
So then root cancels out with power, leaving us with x minus 6 is equal to. Now, here's what a lot of you just messed it up. You messed it up right here. When you take the square root of 9, what does it really mean? Doesn't the square root of 9 mean what squared is 9? Isn't that what the square root means? So what squared equals 9? 3. What else? Negative 3. So shouldn't we have put a plus and minus 3 in there?
Yep.
Does everybody understand why? The square root of 9 is plus and minus 3. So when solving, you have to put a plus and minus. Now even from here, some of you got that far and still messed it up. So everybody, from here, what do we split it up and say? So we have x minus 6 is equal to 3. And we have x minus 6 is equal to negative 3. Does everybody understand how I just split it up? So then from there, solve for x. So we would add 6. Our first answer is x equals 9. Now a lot of you just said, oh, so negative 9. Not true. To go through the algebra, people, what do we do to solve for x on this one? Add 6. So x is equal to positive 6 minus 3? 3. How many got 100% correct? Good job. Okay, how many of you now see what error you made and you will not make it if I gave this problem in a few days as a bell quiz? Okay. Okay. Well, if you got the answers right, then you did something right.
I did. I kind of spaced it, didn't split it up a bit.
Okay, let's get going. So this is our unit of circles, guys. Circles is hugely going to help you with your ACT, especially where a lot of you didn't get a whole lot of circles last year, because this is hugely important. So this unit is going to help you the most with your ACT coming up. Okay, so today we're doing 7-4. We're going to be dealing with chords and arcs. Now there's a lot of theorems we're going to be using today. I gave you a sheet, so you might want to just write down a couple little notes to yourself on what I'm saying here, because sometimes it's a little bit wordy, so I just reworded it in a little bit more simpler terms. Does that make sense? Because why have it wordy? Okay, so the first theorem. So we're just going to go through the theorems. Guys, pay attention. You're going to use these theorems, and you need to have them in your mind of how they work. So Theorem 79 and its converse. So first of all, what Theorem 79 says, and I just wrote it in a more simpler term, is central angles that are equal, which aren't central angles equal sometimes, right? If they're vertical, guys, right? So if central angles are equal, they will have equal arcs. So look at my picture. If you have central angles that are equal, do you see how I drew a red line saying they're equal? We will have equal arcs, which let's think about that. That makes sense, right? Those central angles equal their intercepted arcs. So if you have a 30 degrees and a 30 degrees, aren't the arcs 30 degrees? Makes sense. So that theorem just makes sense. Okay, now converse means kind of the opposite, so it goes backwards now. Converse means backwards. So, with that being said, if you have two arcs that are the same, then their central, or their angles will be the same. Does that make sense, everybody? Okay, so that's your first theorem. So, your worksheet's a little bit wordier. If you want to kind of draw in your picture what I did, that might help you. Okay? Next theorem we're going to use is, if central angles are equal, they will have equal chords. So, look at my picture. We have central angles, and these ones are vertical angles, or they're equal angles. So if we have equal central angles, then their chords will be equal. Now remember that chord means it intersects the circle in two spots that's not going through the center of the circle. That would be a diameter, right? A diameter is not a chord. So do you see how this blue line intersects the circle in two spots? Okay? It's a chord. It's not going through the center. All right, so if you have two central angles that are equal, then their chords will be equal. Does everybody see that? Yes or no? So with that being said, the converse says if you have two equal chords, then their central angles will be equal. They go back and forth. So if you're given one, you know the other. If you're given one, you know the other. Does that make sense, everybody? So that's your next theorem. You have that on your sheet. Okay, so next one says equal chords have equal arcs. So look up here. If this chord is equal to this chord, then this arc will be equal to this arc. So the converse says, if this arc equals this arc, then this chord must be equal to this chord. Is everybody good with that? Okay. Okay, next one. Now, really pay attention to this one. Okay, chords equidistant from the center are equal. So chords equidistant from the center of the circle are equal. So everybody look at this picture so I can help it make more sense. Okay, so does everybody see how we have a chord and we have a chord? Now look, from the center, do you see how we have a line drawn to that chord and a line drawn to that chord? Now notice they have a tick mark on the chords. So, on that line and that line. So do you see how that line must equal that line? So they're equidistant from the center. Therefore, that blue chord must be the same length as that blue chord because they're equidistant from the center. Does that make sense? Everybody. Do I need to say it again, maybe? Yeah? Okay. So the converse is also true. If you're given these chords are equal, then they must be equidistant from the center of the circle. So given the blue lines are equal, we know that that line to there and that line to there must be equal. Does that make sense, everybody? Okay, we're down to the last few, then we're just going to start applying it. Okay, so Theorem 83 says, if a diameter is perpendicular, so if a diameter is cut perpendicular, now perpendicular, anytime you see the word perpendicular, you say to yourself, I know that means 90 degrees. So we have a diameter. If it's cut at a 90-degree angle, meaning the diameter is perpendicular, then it cuts this chord into two equal segments. So do you see how we have this line that's perpendicular, that's a diameter? We know for sure it's cutting that chord into two equal pieces, as well as cutting that arc into two equal pieces. Now, the word bisects means cuts into equal pieces. So it says it bisects. So if you read this, it says in a circle, if a diameter is perpendicular, 90 degrees, to a chord, do you see how it's 90 degrees to our chord, everybody? Then it bisects the chord, meaning it cuts the chord into two equal pieces. And the arc is bisected, meaning the arc is cut into two equal pieces. So a couple words to keep in mind. If you ever see in the future, perpendicular, you know it means 90 degrees. That's really going to help you on the ACT. Also, if you see the word bisects, you know that is cut into two equal pieces. Okay? So I'm just trying to help you out with some math for your guys' future. Okay. Now, Theorem 84 says, so if you have a chord, so this is kind of this is definitely the converse, I would say. It's its whole own theorem, though. So if we have a chord cut into two equal pieces, then that diameter must be must be a 90-degree angle, meaning it's perpendicular. So if this chord is cut into two equal pieces, then that line must be perpendicular. Does that make sense? So it is just the converse. Are we all good with that? Okay. Last one, then we can just apply all these theorems. So they're not really hard, it's just remembering all of them and not forgetting them. And being able to use them. Okay, so the perpendicular bisector will go through the center of the circle. So if we have a diameter, if we have a line and it's perpendicular, meaning making a 90-degree angle, then it definitely will be a diameter, meaning it will go through the center of the circle. So if it is a 90-degree angle, that has to be the diameter. Does that make sense? Everybody. Which means it goes through the center of the circle. Okay, questions on that? So if we have a circle that's a diameter, it's going through the center and it's bisecting, then that's definitely a 90-degree angle. And it's cutting. So do you see how it's telling us in this picture right here that these two pieces are equal? So we know for sure if these two pieces are equal that that's 90 degree, right? Okay. Because that's how they go hand in hand. Okay, so let's answer these questions real quick. So everybody look up here with me. It says, what can you conclude given this picture? So hopefully you can kind of see a couple things about this. What can we conclude? So first of all, notice we have this line is red and this line is red. So that must mean that they're trying to show in color that those are equal, okay? So we know, this is what we know. So I'm going to write it down. We're kind of showing some kind of proofy type stuff today. We know that chord BC is congruent. Now congruent is with an equal sign and a little squiggly above. Is equal to chord DF. Does everybody agree with that? So that's what we know. So from that statement that we know, that was given. What can we conclude? So now I'm going to do a little dot. What can we conclude? So look at your theorems. So one, I'll give you your first one, guys. But I'm gonna have you need to participate today. Don't we know if the chords are equal, then their arcs will be equal? Okay, so we know for a fact that arc BC is congruent to arc DF. Can anyone tell me what theorem that was really quick? On your paper-ish. One. Theorem what? 80. Theorem
79.
Okay, so I'm just going to write that. Theorem 79. Okay, so we're kind of doing a proofy type thing, but it's not really a hard proof, right? You're given the theorem. Okay, what else can we conclude?
So we have right down in
I want you to, I mean, it wouldn't hurt. I probably would, I don't know. I'm debating. I'll think about it next couple minutes. Okay, guys, what's another thing we conclude? Can we conclude that if a chord's equal to a chord, aren't the angles equal to the angles? So can't I say angle O is congruent to angle P? Which theorem's that? Tell me, guys, if we go this slow, we're never going to get through this lesson. 80? Sweet. Isn't that pretty much what we can conclude from this? Okay, so moving on. Okay, let's conclude some things about these pictures. So in picture 1, we're given that angle A is congruent to angle S. So from that, what can we conclude? Can we conclude that chord BC is congruent to chord YZ or ZY, right? Okay. What theorem was that? Okay. And then what else can we conclude? If an angle is equal to, won't the arcs also be equal? Because if we know that the chords are equal, aren't the arcs equal? For sure. So we can also say that arc BC is congruent to arc YZ. Okay, moving on. Let's do number 2. So we're given that angle F, now there's 2 circles here, is congruent to angle K, right? So what do we know about chord ET is congruent to LM, right? Chord LM. And so arc ET is congruent to arc LM, correct, everybody?
Yep.
Okay. So pretty simple, right, everybody? We don't have to do a whole lot of math, it's just kind of applying it. Okay, couple more. So it says, what's the value of X? And you have to justify your answer. So let's look at this and see if we can think through how we can find X and know it for sure using one of our theorems. Okay, guys? Today it's kind of about proving, because yeah, this is easy math. It's about being very specific. So let's figure out. We're looking for X, which is this, right? Okay, so looking at this, can anyone think of a way we can prove for sure that what X is?
They're in 83. Or, no, 82.
Okay, so
X has to be,
you're saying it's equidistant.
yes.
How, but it didn't, well, there's no line saying they were equidistant, so how, you're not wrong, but how do we know for sure they must be equidistant? Yeah.
Because since the equidistant across, then we have a 90 degrees on both sides.
Because
The theorem didn't say anything about the 90-degree part.
plus 18. is
Oh!
So if those two are equal, then they're both equal.
Okay, you're right. Oh, you're saying that this chord is what, 36? What's this chord?
36.
36, therefore, if a chord's equal to a chord, aren't they equidistant from the center? So you would say, because the chord equals the chord, then they must be equidistant, so then equidistant from the center, correct? Isn't that true? They're equidistant from center, thus, X must equal, X must equal what? 16. Questions on that? Okay, couple more, then I'm going to let you go. Okay, find the value of X.
the same thing. They're both equidistant.
Okay, so you're saying this is 5 to this chord, this is 5 to this chord. So the chords are equidistant.
That's like 7, and it's saying that those two sides are equal, and that equals 14.
Okay. So chords are equidistant from center, equidistant. So guys, stay with me. From center. Thus, x must be equal to that chord, right? Which is 7 plus 7, which is... But do you see how I have... Yeah, you have to state why. So the math's not hard today because it's a proving it. Okay? Questions on that one? Okay, so once again, last one, then I'll let you go. How can we prove this one correctly? What do we know?
The lines are...
So you're saying that this chord is equal to that chord because of the lines. You're right. Thus, they're equidistant. So chord is equal to chord. Thus, equidistant. I'm going to just scribble that. So, x must be equal to 8. Questions on that? Okay, go. 1 through 7. For x. Okay, so you can use whatever you know from the picture. You can use any theorem you like. These pictures are pretty straightforward, though, for the most part. So looking at this, it says find the value of x. So notice a couple of things here. We have a diameter of 20, right? Everybody? We don't have 2 chords or anything with this one, right? No 2 chords, okay? So we have a diameter cutting it. So what's our radius?
10.
So this is 10, this is 10. Okay, interesting. And then we have this chord, which is 16. Now also we have this line cutting down, and it's making a 90-degree angle. And then we're asked to find x. So x is this segment, right, everybody? Okay, so I'm going to change colors. Let's really think about this. If I draw a radius anywhere, will that work? Yeah? So let's think about it. Couple things. So if I have a radius from here to here, it's 10. Now if this is 90 degrees, well, isn't that a straight line angle? So won't this also be 90 degrees?
Yeah.
Now let's think about it. If we have a line being dropped perpendicular, meaning making a 90 degrees, doesn't it cut this into 2 equal segments, a chord? So the whole thing, did you say what? Okay. So we have this whole thing 16, what would this be? 8. Now look, don't we have a right triangle?
Yeah.
So let's set up, I'm going to redraw my right triangle here. So I have, this side is 8, right? This side is x, right? Our hypotenuse is across from the 90 degrees, right? So that's got to go here. Now, to find missing sides, I'm going to draw my 90 degrees. To find missing sides only of a right triangle, can't we use the Pythagorean theorem? As long as it's right, you can use the Pythagorean theorem. Now, I'm going to ask a question. Can you use the Pythagorean theorem to find missing angles of a triangle? No, right? That's only a side theorem, okay? So everybody remember that, okay? Okay, so we have to do it correctly. Can we go 8 squared plus 10 squared is equal to x squared? No, that's like really bad news, right? Doesn't the hypotenuse always have to be on the outside of the equation?
Yes, okay.
So we go x squared plus 8 squared is equal to the hypotenuse squared. So everybody understand? So we have x squared is equal to 10 squared minus 8 squared, right? I subtract 8 squared from both sides. Is everybody good with that? So we have x squared is equal to 16. 10 squared is 100 minus 64. Okay? And then from there, what will we do to solve for x? Square root it. So we have x is equal to plus and minus 4, right? Do we throw out the negative 4? Doesn't make sense to have a negative 4 side length, right? So x is equal to, oh, it's 36?
Yeah.
Oh, yeah. 36, not 16. 36, not 16. Okay, 36. Sorry, 10 squared. Yeah, 36, not 16. In my head, I was doing that weird. Okay, so the square root of 36 is 6. Plus or minus 6. We throw out the minus, okay? So x is equal to 6. Is everybody comfortable with that one?
Yep.
Okay, let's do another one. Okay, looking at this picture over here. We're like, this is what we're trying to find, our radius, right? But we have no idea, like we have a piece of a radius, right? We don't have enough information to keep going. But couldn't I draw a radius anywhere? So couldn't I go right there and call it x?
Yeah.
Isn't that the same thing? Is everybody paying attention?
Yeah.
Okay, and then also we know, okay, so we know this side is 3.6. Now look, because the chord is being cut at a 90-degree angle, this side must be equal to this side. Therefore, this side is 4. So now we just have a right triangle again. We had a 4, we had a 3.6, and an x, right? So 3.6, go, calculator. 3.6 squared plus 4 squared is equal to the hypotenuse squared, which is x squared. Go.
20.96.
Is the final answer that, or is that just the squared? I'm just curious. That's this part, that's what I want.
Equal to x squared.
Okay, what's equal to x squared? That's what I want.
Yeah, that's 28.96.
0.96 is equal to x squared. Then we'll square root it, right? So x is equal to, round to 1 decimal place, because look, our picture had 1 decimal place, that's why we go with 1 decimal.
So,
If you would all help, we'd get to the lesson 10 times quicker.
5.4.
5.4.
yeah.
So x is 5.4. Questions on how to do those? Okay, last couple, and then the rest of the time is yours to work. So it says, just ignore this. So the question is, it says, how does auxiliary how does auxiliary BA make it simpler to solve for y? So how does this line make it simpler to solve for y? You tell me. How does that dotted line help me solve for y? It's a right triangle, right? And don't we know this radius is? And then from there, isn't it just a right triangle true? So that's what you'd say with something like that, okay? Okay, last one. Word it a little differently, but let's use our brains for a minute, okay? You have to be able to see things in different contexts and go. Okay, so it says, in the diagram at the right, the endpoints of the chords are points where line, in the diagram at the right, the endpoints of the chord are the points where the line x equals 2 intersects the circle. X squared plus y squared is equal to 25. So let's decipher what this is saying. Does everybody see the chord?
Yeah.
Okay, so we have an XY chart here. We have a chord drawn. Now, chord means it touches the circle in 2 spots as long as it's not going through the center. There's our chord. It's at the equation x is equal to 2. Does everybody see how this is an x is equal to 2 line? Okay, now it intersects the circle at x squared plus y squared is equal to 25. So you have to know the equation of the circle is x squared plus y squared is equal to the radius squared. Okay, so looking at this, this is our circle drawn. They've drawn it for us. So our radius is 1, 2, 3, 4, 5. Does everybody see that? Which makes sense, because if radius squared is 25, the radius must be 5. Okay, so we have this picture here. It says, what's the length of the chord? So we want to know this entire length. So first of all, can anyone see how we can go about doing this? Think. Go, think. You know, we've just been doing it. Okay, talk to your group and decide how could you maybe do this. Go, go, go. Okay, let's try and talk through it. So you said make a triangle. I like the idea of making a triangle. So what's some ideas here? What can I do? Yep, Mason's, you're right on. Okay, so Mason's saying, can I go from the center of my circle and draw a line out to the line x equals 2? Isn't that a radius, people? What is my radius?
3.
5.
Oh, yeah.
Right?
Yeah.
1, 2, 3, 4, 5. Does everybody see that?
Yeah.
Then from here, what's that distance, people?
2.
2. Now, can't we find this piece?
Yeah.
Then from there.
Yeah.
So then, and once again, we know because this is a diameter drops to a chord, that's definitely 90 degrees. So don't we just have a right triangle? So we have a 90 degree, we have a question mark here. Our hypotenuse is 5 and our side's 2, right? So we would do 2 squared plus question mark squared is equal to 5 squared. So we have question mark squared is equal to 5 squared minus 2 squared, right? So question marks equal to what? 4.6. Okay, so now you know question marks 4.6, guys. So when you add that up twice, if these are cut evenly because of the 90 degree angle, 4.6 plus 4.6. Okay, is everybody comfortable with that? That was easy. I mean, way to think through that, Mason. Good job. Okay? All right. Okay. What's the error in the diagrams? Then I'll let you finish up the worksheet. Tell me, what is the error? Perfect. That's exactly said. So these are equidistant, right? Thus, the chords have to be equal, right?
Yeah.
Are the chords equal? Nope. So that's what you would say. So chords must be equal because they're equidistant. Okay, guys. So you're going to finish up the worksheet up to 17. After 17, you can cross them out.
Oh, thanks.